All right, here's the conclusion of section 9.4. This is 9.4c. This is on division and rationalizing denominators in radical expressions. So an expression that has a radical, be it like a square root, cubed root, fourth root, things like that, in the denominator can be further simplified by rationalizing the denominator. So that's how we're going to do this division. We're going to do this by rationalizing the denominator. Now you might have seen some of this before in previous classes, but this technique multiplies the fraction by 1. Now I put that in quotes because this 1 has to be kind of specially chosen, and I'm going to show you the kind of witchcraft involved in choosing this correct 1. And what it's going to do is rewrite the fraction so that there's no radical in the denominator at all. Now what we're going to do is we're going to rationalize the denominator in 3 cases. We're going to have the single square root in the denominator, a single cube root in the denominator, and then a binomial in the denominator. So I'm going to look at these in 3 different cases. So case 1, a single square root in the denominator. We're going to divide and then rationalize and simplify. So I don't want to overwhelm you too much stuff at once here. The square root of 14 over the square root of 6. Now I showed you all the behind the scenes things here, but let me just show you that if you hit the fraction button, we do the square root of 14 on the top and then the square root of 6 on the bottom, you'll see that our calculator simplifies these for us. The calculator will rationalize it for us. But I wanted to show you the behind the scenes action because I think it's good to see this for the numerical things so that maybe it'll make more sense when we do this with variables. Okay, when we have a single square root in the denominator, we're going to multiply by that square root over itself. Now what that does is gives us the square root of 84, that's 14 times 6, and then this is the square root of 6 times the square root of 6, which is the square root of 36, or just 6. So we get rid of that radical in the denominator. This root 84 does simplify further into 2 root 21, and then you'll see this 2 over 6 reduces even farther. But let's be honest with each other here. If these are just, regular old numbers and square roots, just use your calculator for it. You don't have to do that by hand. All right, so let's throw in a variable and see what happens. Now, another approach that we can take is not rationalizing it immediately. Instead, like with this one, we can pull this together into one radical. So we have the 16x and the 4x under the radical together being divided. And look, 16 divided by 4 is 4, and those x's divide out. So we're just left with 4, the square root of 4 over 1, which I didn't have to write the over 1 business. The square root of 4 is just 2. I could have done this in a similar way. All right, I just kind of tackled that one in a slightly different approach there. Right. The square root of 4x over 3y squared. All right, so with this one, if I split all this up into the square root of 4, the square root of x, the square root of 3, and the square root of y squared, how does that help me? Well, it helps me because the square root of 4 is 2. And the square root of y squared, the square root and the squared undo each other, and I just get y. So I get this square root of 4 is 2, and this square root of y squared is just y. So this expression can be simplified into this one. But we're not quite done. How do you know we're not done? Well, if there's still a radical in the denominator, then you're not done. So in order to get rid of that radical in the denominator, I have to multiply by 1. That 1 comes in the form of whatever this radical is in the denominator over itself. So this is 1 because it's something over itself. And you know, if you take something and you multiply by 1, it doesn't change the value, right? 7 times 1, still 7. 18 times 1, still 18. So it doesn't change the overall value of this. It just like throws lipstick and a dress on it, you know? So it just makes it look a little different, but it's still the same expression, you know? So in doing this, I get 2 root x times root 3. I can combine those into a root 3x. And then the y, root 3 times root 3 is root 9, which is 3. Now if you want to skip this root 9 business, you could just say, hey, the square root of 3 times the square root of 3 is going to do just like this. The square root squared is going to undo each other, and you're just going to get 3. But I just wanted to show you all the behind the scenes things. Don't cancel those 3's. Why not? Well, because one of them's under a radical and one of them isn't. So if this 3 were on the outside, then yeah, by all means, you can cancel them. But because one's under and one isn't, you can't cancel them. So to rationalize a square root in the denominator, so that's my abbreviation for square root, you multiply by that square root over itself. So there's our abbreviation. Is that looking fuzzy to you guys too? I don't know why my camera's struggling to focus here. Seems to be focusing fine, like right here in the middle, but on the outskirts it looks a little fuzzy. Sorry about that. Okay. The last one for case 1. Square root of 25a over the square root of 4ab. So I'm going to pull this together into one square root here. Now the reason I'm going to do that is because I already see that those a's are going to cancel. Because that one's under a radical, that one's under a radical. So I pulled those together, canceled those out, and then I went and like separated them back again. So, you know, in hindsight, maybe I could have just written this as square root of 25 times square root of a over square root of 4, square root of a, square root of b, and then canceled the square root of a's. I could have taken that approach too, but here we are. The square root of 25 is just 5. The square root of 4 is 2. So look at how much nicer that is than what we started with. But we're still not done. We still have to rationalize it. You can't have a radical in the denominator. So because it's a square root, I'm going to multiply by that square root over itself. That's the 1 that I'm multiplying by. So what that's going to do is give me 5 square root of b on the top, and then 2, and I get the square root of b times the square root of b, or the square root of b squared, and those undo each other. That's purposeful. That's not an accident. That's not like, oh yeah, that's kind of cool. No. We just forced that to happen. By multiplying by the same thing, we forced that squared, which then undid the square root. So then we get just b. Don't cancel those b's. One's under a radical, one's not. Don't get all canceling crazy on me, okay? All right, case 2, a single cube root in the denominator. This one's a little trickier. So your calculator is not going to simplify these like it will square roots. Okay? I'm sad to say, because you know it's pretty awesome that our calculator does all the square root simplifying stuff. I really totally dig that about this calculator. For the cube root, we're going to have to work harder. So first up, I'm going to take this fraction, 32 over 20, and I'm going to reduce it. It reduces to be 8/5. So just in case you don't remember how to reduce a fraction, 32 over 20, you hit enter, boom, there you go. So it reduces to be 8/5. All right, so now at least we have smaller numbers to contend with. We have the cube root of 8/5, which is the cube root of 8 over the cube root of 5. Now, yeah, the cube root of 8 is going to simplify to be 2. If you see that immediately, awesome. I do get there eventually. But here's the 1 that I have to multiply by. That 1 is the cube root of 25 over the cube root of 25. Now, you probably look at that being like, did she just yank that straight out of her butt? No. There's actually a reason why I chose the cube root of 25. That's because down here, I explain it. Here we've got 5. Here, I wanted to multiply by something that was going to form a number that's a perfect cube. All right? So you might be saying, what does she mean by perfect cubes? Well, perfect cubes are numbers like 1 times 1 times 1, 2 times 2 times 2, 3 times 3 times 3, 4 times 4 times 4, 5 times 5 times 5, 6 times 6 times 6, and so on. Those are perfect cubes, just like the perfect squares. You are 1 squared, 2 squared, 3 squared, 4 squared. So I wanted to multiply 5 by something that was going to make it a perfect cube. Now I chose 25 because I saw that this was 5, this is 5 squared, so multiplying those together is going to give me 5 cubed. And the cube root of 5 cubed is just 5, because that cube root and that cube undo each other. So that's why this one is trickier, because you seemingly have to pick a number straight out of your butt to multiply by. But hey, the good news is, if you choose correctly, everything works out great. So we get this cube root of 25 up top. These combine into the cube root of 125, which is just 5. Now you may be like, how does she know that? Well, because 125 is a perfect cube. So remember, for a cube root, we have to hit 3, second, and then the x root. And the cube root of 125 is just 5. It's helpful when you're doing these to keep this list of perfect cubes handy. All right, so that's a really helpful thing to keep nearby. So here we go. There's my final answer. Don't try to cancel that 25 and that 5. That 25 is under that cube root. That 5 is not, so those cannot cancel. So we got the cube root of 7x over 4. This is not going to reduce. Extend that a little bit more. It looks like it stops there. The 7/4 doesn't reduce, so there's nothing really we can do except go ahead and work on rationalizing it. So I need to multiply by something. There's my 1. So that this number under the radical, remember that's called the radicand, it's also sometimes called the argument, something that I need to multiply 4 by that will give me a perfect cube. So let's go back to that list of perfect cubes down here. Oops, sorry about all the flipping here. So 4 times what will give me a perfect cube? Well, 4 times 2 is 8. Or you could say, hey, I can multiply 4 by, I don't know, 16 and get 64. So yeah, there are others, but hey, that one's the smallest. So that one will simplify a little faster. So I picked 2 because I saw that 4 times 2 was going to be 8, and 8's a perfect cube. So this gives me the cube root of 7x times 2. So 7 times 2 is 14. 4 times 2 is 8. The cube root of 8 is 2. And this isn't going to simplify any further. That's because 14 doesn't have any perfect cube factors. And you can't cancel that 2 and that 14 because that 14 is under that cube root. So the stuff that I just said, I wrote out. You're going to rationalize a cube root by multiplying by the cube root of a number that will make the radicand a perfect cube. And see, there's the list of perfect cubes there for you. It's a quick reference guide. So let's look at the cube root of x to the 5th over the cube root of 9. Now don't get crazy on me here. Don't be like, oh, the cube root of 9 is 3. No, 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 no. You're thinking of division. You're thinking of 9 divided by 3 is 3. So let's look at these perfect cubes and let's ask ourselves, what's the smallest one that I can multiply something by 9 and get one of these numbers? Well, how about 27? I see you, 27. So if I multiply that 9 by 3, I'll get 27. So that's the one that I'm going to pick. I'm going to use the cube root, and 3 is what I chose because 9 times 3 is 27, and 27 is a perfect cube. So multiplying these together gives me the cube root of 3x to the 5th. I smush those together. This gives me the cube root of 27, which simplifies to be 3. Oh, but wait a minute. This one, this cube root of x to the 5th, this simplifies further. Oh yeah. Remember earlier in this section? Oh yeah. That stuff's coming back, baby. It's making a comeback. So, I did this in blue to show you what's going down. Refresh your memory here. Remember this? Oh yeah. The cube root of x to the 5th, remember how we did that? We divided exponent over root, so we took 5 divided by 3. So 3 goes into 5 one time with a remainder of 2. So there's my quotient of 1 and my remainder of 2. So that simplifies to be x, and then that's x squared under that cube root there. So I did this stuff in blue, so you can see I kind of wrote that in blue. I did all my side work in blue, and then I put this answer in blue. So this cube root of x to the 5th simplified to be that x cube root of x squared. Now, what about those 3's? Well, that 3, just along for the ride. That 3, same thing, along for the ride. So you can see how these can get out of hand really quickly. You know, a lot of stuff happening at once. You've got that rationalizing, you've got some simplifying or reducing fractions, and then you got to come up with this number. You know, you got to pull this number out of your butt so that it just kind of works out. You know, it's just, it seems like a lot of mathematical witchcraft, but it's not. I assure you, it's not. I kind of like to think of it like, you know, a cool little puzzle, but I don't think I'm normal when it comes to that. I don't think normal people look at this stuff and are like, oh, that's kind of cool. So, all right, let's look at one more of this case. So we've got this cube root of x over 2y squared. Oh, Lord. So now we've got to figure out what to multiply 2 by to get us a perfect cube. All right. 8's a pretty common one that you're going to see. It's a perfect cube that you know, happens a lot in the Hawks homework. So I picked 4. Because 2 times what's going to give me a perfect cube? Well, 4. It's going to give me 8. Oh, but then we got this y. What do we do with this y? We just need that exponent to be a multiple of 3. So this, I chose y to the first because this y squared times y to the what will give me y to some multiple of 3. Why a multiple, you know, multiple of 3? Why do you think I pick a multiple of 3? Because the cube root of some multiple of 3, that's going to divide out and simplify so that that cube root goes away. So it's not like I just, you know, made that up. That's, you know, very intentional. So y to the first. So y squared times y to the first gives me that y to the 3rd power. All right, so let's look at what happens here. The top stays the same. Nothing really happens here. But the bottom, we get this cube root of 8, which is 2. And then look, the cube root of y cubed, that cube root and that cubed undo each other, and we just get y out of it. So I hope that I did kind of one of each, so that no matter what scenario you run into in Hawks, that you have, kind of a guide to follow with those. Okay, case 3. Now, fortunately, this is not the worst one. Case 2 is definitely the worst. This one is a binomial in the denominator. Now, binomial means 2 terms. Okay, so here we're going to have 2 things happening in the denominator. To rationalize an expression that has a binomial in the denominator, we're going to multiply by the conjugate. Now, what's the conjugate, you ask? Well, I wrote up a bunch of binomials. So look, they each have 2 terms. And then their conjugates. So this is the binomial, square root of 2 plus 1. Its conjugate is the square root of 2 minus 1. Negative root 3 minus 8, the conjugate is negative root 3 plus 8. So if you look at this, you'll see the conjugate just changes the middle sign. That's all it does. So no big deal. We just change the middle sign. All right. So we're going to rationalize this by multiplying by the conjugate. Now I'm going to show you why the conjugate is so awesome, and it has to do with the distributive property and those inner terms. So here it is. You can't just, simplify this. You can't multiply by root 2 over root 2 because of this plus 1 in here. It's not going to get rid of that radical in the denominator. So we're going to multiply by the conjugate. So here's the conjugate of the denominator. Sorry, when I wrote multiply by the conjugate, I should have been more specific here and said of the denominator. Okay, so my conjugate is root 2 minus 1. All right, distributive property. Going down here. So, distributing all this out, tried to color code it for you. So we're going to get 5 root 2 minus 5 times 1, which is just 5. Root 2 times root 2 is root 4. So we get those 2, simplified to be root 4. Negative root 2 plus positive root 2 minus 1. And look, those are the same thing, they just differ by a sign. So those subtract off and give you 0. Those are like terms. So I end up with the square root of 4, which is 2. So we get 2 minus 1, which is just 1. And that 1 down there is not necessary. So we can just write it as 5 root 2 minus 5. All right, so let's back up a skosh here. Let's do 5 over root 2, get out from under the radical, plus 1. Check it out. 5 root 2 minus 5. So without a variable, see, no letter, you can do this on your calculator. Did want to show you all the behind the scenes things, all the stuff the calculator's doing, but that's what's going down here. Okay? Of course, this does not work when you bring in a variable, but you certainly can just use the calculator here. Alright, so this one, I chose to use numbers for this one, okay? I did not use variables on this one, but I am not going to just put this one in my calculator. I do want to show you all of this because if we start throwing in variables, I probably should have, although I'm not sure if Hawks has any that have variables to it, but we'll see. You'd have to multiply by the conjugate of the denominator. So you multiply by the root 7 plus root 3 over itself. When you distribute all this out, you're going to have to FOIL the top and the bottom. So I tried to color code it so you could see. But I mean, look at all this. This is a hot mess in here. If I start throwing in variables, then this gets a little bit messier and can't be done on calculator. So let's just go through this with numbers while it's still a little bit easier. So we get this root 5 times root 7, root 5 times root 3, 3 root 7, and 3 root 3. The bottom, root 7 times root 7, root 7 times root 3, minus root 3 times 7, minus root 3 times positive root 3. Now we start grouping these products together. Each one of these little pairs that's multiplied, we can simplify them. That'll be root 35, root 15, 3 root 7, 3 root 3. Down here, I get root 49, root 21, root 21. That one's got a minus though. And then root 9. Those subtract off. That always happens when you multiply by the conjugate. And then the square root of 49 is 7. The square root of 9 is 3. So that's just going to be a 4 down there. And because none of these are like terms, and they don't simplify any further, there's nothing we can do with those. Alright, let's just see. I'm just curious if the calculator will do one a little bit more complex like this. You and I are about to be surprised together, because I honestly don't remember if the calculator will do these. So, moment of truth. Ooh. Ooh, look at that. It does not simplify one that complex. I was afraid of that. So it did simplify one that was a little bit nicer, like this. But as soon as it got a little more menacing, your calculator did not help. So, yeah. If you try to put this answer in Hawks, it's not going to accept it because it wants the exact answer, not an approximation. Alright, so it's important that we multiply by the conjugate of the denominator. Don't accidentally multiply by the conjugate of the numerator. We need the conjugate of the denominator. That way, these middle terms go away. My radical terms go away in that denominator. So you can see how I don't have a radical in the denominator anymore. Alright, so that finishes section 9.4c.